Hi, this is the presentation of my project final report. So, in the phase 1 of the project, we had to simulate the trajectories of molecules while unfolding. Meanwhile, in phase 2, we were required to find the PMF, the potential mean force, as well as understand and verify the Jarzynki's equality. So, starting off, what is the Jarzynki equality? According to Jarzynki equality, the free energy difference delta F and the work W done on the system are related by the following inequality: delta F less than or equal to W. This equality also goes on to state that the delta F is equal to W for reversible or even quasi-static work. It also utilizes the Jensen inequality, which states that delta F is less than or equal to the mean work done. From Jarzynki's equality, we can also show that the change in free energy is path independent. Next, coming to the aim of the project. This project seeks to verify the Jarzynki equality by calculating the mean force potential or PMF using the trajectories that we obtained from steered molecular dynamics SMD. So starting off with the procedure of phase 1. So first we use the CHARM GUI to generate the corresponding protein structure file for the protein molecule allotted to us. So the protein ID allocated to me was 4H6S underscore A. So using this PDB file, we had to proceed with the following steps. So in the CHARM GUI, we need to select the quick MD generator and upload the allotted .pdb file. In our case, it's the 4H6S underscore A .pdb file. Choose the option for terminal patching. Download the tar.gz archive, which contains the PSF and .pdb along with the parameter files which NAMD needs. Modify the file names of the .pdb and PSF files in the smd.namd file. Also modify the atom selections in the smd.tcl file. The simulation was done at 300K for 50,000 time steps. The simulation was run using the following command: namd2 smd.namd t log. This procedure produces the output files log, the log file, da underscore smd.dcd, the trajectory file, da underscore smd.tcl.out, the TCL script output. So here the da underscore smd.dcd is the file that we give to VMD for the simulation part. So as we see from here, after phase 1, this was the extension versus time graph that was generated. From here, we can get an idea of the trajectories of the molecules while unfolding with respect to time. This, on the other hand, is the force versus extension graph. Next, we move on to the procedure for phase 2. So here we start off by changing the velocity value in smd.tcl to 0.00002 per time step, which for 500 time steps in picoseconds comes out to be 0.01 angstrom per picosecond. This is called the pulling velocity, this value. This value is also good for doing reversible work. Next, alter the number of time steps simulated to 100, that's 1 million, that is for 2000 picoseconds. In the next step, plot 3 trajectories using these values and store them in the traj1.out, traj2.out and traj3.out. So then generate the da.dat by running the makedat.py Python script. So next, generate the extension versus time and force versus extension graphs. So here we have the extension versus time graph for my molecule. So my understanding of these results was that it shows a clear picture of how simulations work. There is also a certain randomness to its motion during the simulation. Next, this is the force versus the extension graph For force also, there's a certain zigzag pattern over here that we can observe. And this is the PMF versus extension graph, where this is the F1 and this black line is the FXP. So in this graph, we can see clearly that the F2 value is going down or below the axis, while F1 and Fx keep going above the axis. Now I'm going to compare with two of my other friends. So for the first teammate, this is the extension versus time graph that he had found. This is the force versus the extension graph in his case, and if you notice carefully, in mine it was somewhere at the bottom while his is entirely at the top. Then as we can see over here, this is the Fx, this is the F1. Here again the F2 is going below the axis. Now for the teammate 2, again this is a very similar extension versus time graph that all three of us have gotten, but the force versus extension graph is highly similar to mine, except it contains lesser zigzag than mine. And again, this is a slightly different graph, starting off steeper and then stagnating considerably more than mine or my first teammates. So again, this is the Fx value and this is the F1 linear slope. Next, here we have the F2 value, which is again going below the axis. Next, coming to observations. The first observation is in the case of extension versus time. All three sets of graphs are constructed using initial point at 13 and pulling velocity 0.00002 angstrom per picoseconds. So the graphs do not follow straight lines, but does not deviate much if you draw a straight line for trajectory. So this is me, my first teammate and my second teammate. I have listed each of the molecules that each of us were assigned. So again, as mentioned, the starting point is 13 angstrom. In all three cases, a slight difference. So in my case, this is it ends at 32.5 angstrom. In case of my friend, it's 32 angstrom, and for another friend, it's 31 angstrom. And the time was fixed at 2000 picoseconds each. So for finding the velocity, the difference in position by time gave me the pulling velocity, which is approximately 0.01 angstrom per picosecond in each of the three cases. Next, we go to the force versus the extension graph. So the initial part of the graph does not really represent much, as the extension starts from 13a. This is where the graph truly begins. The force does not follow any type of particular pattern. Graphs can be compared using a range of force shown by each graph. Here, as we saw, the force behaves in a zigzag fashion. It's either below the axis or above the axis, but it's always in a zigzag fashion. So here we can see there's always some sort of zigzag action to force, and it only starts somewhere at 13 angstrom, because until then almost no activity taking place. So again, each of our molecules, and the minimum force applied was -5, -5, -5 newtons, and here the maximum force keeps varying. So in my case it's 20, and then in my friend's case it's 13, and for my third friend it's 25. For PMF, each of us used a Jarzynski equality for finding PMF values and plotted it. For every student, for each of us, for all three of us, the F2 value went below the axis, while the other two, Fx and F1, are always above the axis. For all of us, in the first PMF versus the extension graph, the Fx was also always greater than, or had a better slope, or was always higher than the F1 curve. Also, Jensen's inequality states that change in free energy less than work done on system. This observation can also be verified using the PMF graphs that we have observed. So finally, coming to the conclusion, the change in free energy is path independent but can be equal to work done when it is reversible. So we can find change in free energy using Jarzynski equality. For movement at very small velocity, we can say that change in free energy equal to change in work done. I hope all of you have understood my presentation for the project final report, and it's extremely clear.